Hello and welcome to another video. In this video we're going to be working on extra characters in a string. So in this problem you're given a string and you're given a dictionary and you want to say how many extra characters there are in the string that couldn't be broken down into words in this dictionary. So for example, when you're given LeetCode, you can break it down into LeetCode and then there's this extra s, so you would return 1 there. And then for the second one, so for say hello world, you can break it down into hello and world, and this say is extra, so we have 3 extra characters. So the way to do this problem, you can do it one of 2 ways. You can either do just straight DP, or you can make a trie, and then you can make DP. And I'm going to kind of talk about the pros and cons of a trie and show you how to make a trie. So let's first show how to make a trie. So essentially what a trie is it's represented as a data structure, and it has 2 things. So one, it has a dictionary of children, and each child is a letter with a value dictionary, or actually trie. And it also has one more thing, it also has a Boolean for is word or not. And I'll get into that. So essentially what the is word means, like a trie might be the end of a word, but it might not be. And so it's default false, and then it's true when we put words in. So let's see how we can put these words into a trie. And essentially a trie looks like a tree, but it's represented, like I said, by a nested dictionary of tries and a Boolean. That's the data structure. So when you first make a trie, you want to do this. You want to make a root node. Let's actually make this we'll make this. So we'll just represent this, but this is really a data structure of a trie, and like I said, each trie has a dictionary of children and a Boolean is word. So when you're trying to insert leet, what happens is you start at the root, and then you check letter by letter, is it in there? And if it is, you traverse it. If not, you put it in. So you start with nothing, and then you say, okay, is L in this? No, it's not. So we're gonna make L, and that just means that the key here is L, and the value is another trie. So we have to insert a new trie, and then we traverse down to that, and then we say, is E in there? No, it's not. And we're going to keep doing this for the whole leet. So L, E, E, T. Okay. And basically, each one of these nodes is really a trie. It's not a node. I'm just representing them as nodes. And then finally, because you're done with leet, that word is over. So anytime you get to the end of a word, you have to mark this Boolean is word to be true to represent, like when you get here, that means that this thing actually ended. It is a word. Okay, now we're going to put in code, and code is going to be the same way. We're going to say, starting at the root, we always start at the root when you insert. Is a C in there? No, it's not. So we're going to do the same thing. Now the rest of it isn't in here either. So we're going to say C, O, D, E. And then once again, we are at the end, so we're going to mark this thing true. Okay, and there we go. And so that's how you insert into a trie. And then if you tried to insert something like, let's say you tried to insert something like leash, what would happen is you'd go down here, you'd say the L is in here, the E is in here, but then you would branch off here because now you need an A, so you would put in an A, an S, and an H, and so on. So that's how you insert more words, and then once again at this H, you would also mark that as like complete. And with a trie, you don't really need to have the letter because you're just going to be able to basically recurse down into, or not recurse down, but traverse down into the dictionary of the letters, right? So you'd start at the root would have a dictionary of letters. So in this example, the letters it would have would be L and C after we put in leet in code. Well, let's also put in LeetCode, by the way, right? So we forgot about that. So for LeetCode, so we're going to do the whole word, right? So L, E, E, T is in there, but now we have to put in code. So we traverse down to T, and then we're going to put in C. Now there's nothing in here, right? So O, D, E. And once again, this is a new word. So as you can see, in any path, there can be multiple letters that are new words, right? So you can see, like in this path, there's 2 words in here. There's leet, and then there's LeetCode. And so that's how you would make a trie. And then to check for words in a trie, like I said, pretty straightforward. Let's say we're looking for like ball. We can just say, okay, well, can we get the B from the root? No, we can't, so ball is not in there. So anytime you have to get this whole word, and let's say the word was like, let's say cod was a word. It isn't, but let's say, actually I think it's a fish, right? So I think it is. So Maybe it's spelled different. But anyway, so for COD, you would say, okay, COD is in here, but now that we're done with the word, this try has to actually, this thing has to be true, symbolizing that we're done with the word, and it's not true. So not only does the whole word have to be in here, when you're done with the word, the current node you're on, that's why you need this is word value to say, like, this is actually a word. So this would be false for COD, because you can traverse, but this is not blue. So blue is symbolizing that that boolean is on. And now it's pretty straightforward. Now let's say we have like LeetCode. Now we're just going to do a DP solution where we have two options, right? Actually, we have multiple options. So let's show what a DP solution would look like here. So we need the, what do we need for a DP? We need the like values in here, right? So the parameters, I guess. So for the params, we just need the index here in the array. Then we also need the base case. And then for the base case, our base case is going to be when we're at the end of the string. So when we're end of the string, we can't, like, we don't have any more letters, right? So then we can just return 0 because it's asking how many extra characters do we have. And when we're at the end of the word, we obviously don't have any more extra characters. Now we have our recursive case. Let's actually get rid of this. So recursive case, we have one of two options. So A, we can just not take the current letter, right? Like, let's say we were on LeetCode and we were on this L, and we could always like not take the letter and say it is an extra letter, in which case we would just do 1 plus dp of the next state, right? So it's going to be 1 plus dp of index plus 1. And then the other version you have is you can take any word starting here, meaning if you start at leet, you have to actually go through this whole LeetCode thing, like all the way to the end in the try, and until you either run out of bounds of the try, like until you're either done with this whole thing, or until some of your word is no longer in the try, you have to traverse through the whole thing because you can have multiple words in here, and for every word you find, you have to recurse into that word. So essentially, when you go here, you would go down to leet, you'd say, okay, this T is a word, so then I have to recurse down to here, and then check how many extra words are there from here, right? And so you essentially would just update the index to the index of the letter after the word you picked. So here you pick leet, and then you would, you would also have to keep going and then check here as well, right? So in this one loop, you would check both of these. So this would be like a new DP state, this would be a new DP state, but you'd get to both of these from here. So you're essentially doing like a nested for loop here. So that's pretty much it. So you just take any word starting here, traverse the string, any word that's in the try following the string needs to be recursed into with a new state. And obviously, when you give it, for there, you're just literally saying like, okay, I'm going to try to split it into this. I'm going to go over here. Okay, I'm also going to try to split it like this, where this whole thing is at the front. I'm going to go into here and so on. Right? So you can either be out of bounds, or you can either like run out, like let's say our word was ball and we were here. Well, we would say like, okay, let's try to reverse the whole word. Well, B isn't in here already, so we can just break now, right? Anything after B won't be in here either. But we can have something, like leet ball or something. So you would traverse, and then once you get to this B, you would not have to traverse anymore. But worst case scenario, you do have to traverse from the index to the end of the string. And so the nice thing about a try is, for a word like this, if this is 50 characters and each word like here is 50 characters and there's 50 words, using a try, when you start here, you only have to, like for one iteration, you only have to go to the very end here, right? But if you were to compare it to every single word, like without using a try, then you would have to compare 50 times 50 letters for every DP state, because you would have to compare this word to every single word in here. So if they're all 50 words, worst case scenario, you have to compare it to every single one. So as these words, basically, like if you think about it, as this string gets bigger, a try is worse because you have to go through the whole string. But as there are more words and as the words get bigger, a try is better because we're essentially saving time because we're just traversing down our try instead of like comparing this to every word manually. It's a lot more efficient. We just traverse or down our try, compare it to the string, and then anytime we're out of bounds or we're out of bounds of the string or we're out of the try, we can just return. Okay, so let's go through the solution now. Let's code it up. So essentially we're going to make a trie, and like I said, a trie is basically an nested dictionary in Python. So class trie, and it's just going to have an init. It doesn't actually have a letter. All it has is a children, and it has an end. And then we're going to make a root trie, and that's where we're going to start every time. And then essentially you have to go through all these words, and you have to put all of these words into the trie. And the way we're going to do that is you just loop through every word. So we're going to like do this before checking them in the DP. So we're going to say node equals root, and then we have to go through every single character in the word like I showed, right? So for char in word, if char not in trie, we have to put it in, or node.children, the current node. So essentially we are at some node. If the character we're on is in its children, we can traverse. Otherwise we have to add it manually. So node.children char equals new trie. Literally what I showed, you know, where you're inserting the leet in the code. So that part should be straightforward. And then we have node. So essentially now we're traversing one level down. And then we are going to keep doing this. We're going to keep checking, is the new letter in there, is the new letter in there, until we're done with the word. And then once we're done with the word, we have to mark whatever trie we are at to say node end equals true. And this end represents that it is a word, right? So every node that has the end equals true means that is the end of a word. Okay, and now finally we're going to do the DP part. So we're going to say visited this, we're going to say DP index. And what's our base case? Remember, our base case is we're out of bounds. So if index equals length of s, we are going to return 0. If index visited, normal caching. And then finally, let's go through the result. So you can always not take the letter. So we're just going to set the result equal to that. But you might not necessarily be able to divide it up. So we're going to say, let's just set our result to not taking the letter, right? 1 plus just going to the next index if you don't take it. Then we can say node equals root. And then we are going to loop through every single letter from here to the end of the word, or to the end of the string, or we are out of bounds in the trie, and I'll show you how to do that. So essentially we're looping from every single index from here to the end, in range. And we are going to say if si not in node.children. That means like we are trying to traverse down a trie, but we can't anymore. We can just break this loop because we're done. Nothing else will be in here. So that part is straightforward. Let's make a little more space here. And then we're going to say node equals node.children s, right? We're just traversing deeper into the trie. Or yeah. So, and then if node.end, meaning this is a word, then we have to recurse. So we're going to say res equals min res dp this one. And then, so there's another case, like let's say we split up our word and we got 0. Well, if we got 0, we can't do any better than 0. So if we got 0, let's just break this loop because we can't do any better, right? Slide optimization. And then now we're simply going to cache. And we are going to return the result. And then finally, we will call DP on index 0, and we need to be returning that. And let's see. Okay. And there we go. Okay, so the upside of a trie is it is pretty fast. The downside is we did have to make a trie, right? So it obviously takes more space. So that's where, like I said, it kind of depends on your solution. As this words dictionary gets bigger and as the number of words, you know, get bigger, as there's more words, as they're bigger, the trie gets better and better. As there's less words, it's just, you can just compare it to every word because it's a little bit more efficient that way. So it just depends on what your parameters are. So for the time to build the trie, let's just say, what do we want to use here? Let's just say D is the number of all of the letters in this dictionary. So to build a trie takes D because essentially, worst case scenario, all these words are different. Like let's say your words are like ball, fall, and like tall or something even. All of these words start with a different letter. So all of these would be in the trie, which would be all of the letters. So to build a trie takes D, which would be all the letters in the dictionary. And then to go through this DP, essentially for every index, you are starting at some index, let's say here, and you're looping worst case to the end. So that's going to be length of s squared. So that's the time for the trie solution. And then for the space, like I said, we are building the trie. So worst case scenario, you know, you have to be actually, like your trie will have basically roughly d number of nodes, because you're going to put in new nodes. Obviously, you have a root node, so a little bit more. But you could, worst case scenario, if you had 12 letters, you could have 12 nodes. So that's why it's d. And then for the time, or for the space, I guess. So we only have one state here, which is index, which is just length s, right? So even though this is a nested for loop technically, because this is going to take s time and this is going to take s time, for the space, we are only going to have a number for every index, which is just s space. But yeah, so important thing to know about, just know, when is a trie good, when is a trie bad, how is a trie better than just a normal DP as this gets bigger, and then how is a trie better than normal DP as this gets bigger. And once again, as a string gets bigger, obviously a trie gets worse because we are looping through the whole thing. As these words get bigger, and as there are more of them, a trie gets better because we don't have to manually compare the string to every single word, right? But you do have to build it beforehand, so it will take up a little bit more space because of that. But it will save you, time in the future. So it's kind of good when your words are big to easily compare with words quickly and to get all the words you can. But yeah, that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.